Hi everyone, welcome to Biostats 347. This is Lecture 2, Part 4, the last part. So this is a 4-part series, and thankfully, mercifully, this is the last part. We're going to look at, so we covered so far Nyman, Pearson, and Bayes, and we're going to take a broader view now and look at the role of statistics in science, okay? And this whole idea of falsification. So falsification has been around, the idea of, testing our hypotheses. But it really wasn't until a philosopher of science came along and said, yeah, this is how we do science. We falsify hypotheses. And I don't know if you've ever come across, how do you define a scientific hypothesis or what science? It's something that could be falsified. So this idea of falsification has gone so far as to define what is scientific. And the person that kind of led that charge was Karl Popper. So he lived 1902 and he died in 1994. And what he said is, for us to think a hypothesis is a good one, a robust hypothesis, we do our best to prove it false. And if you can't prove it false, so we don't try to prove it to be true, we try and prove it to be false. And if we can't, it means it's a good hypothesis, okay? So this sounds great. And you talk to most scientists and they think this is how the world works. We go out and we try and falsify hypotheses. So I noticed there's a problem with this, is that statistics in and of itself does not offer falsification. So the way that Nyman Pearson works is that you have a null hypothesis and you reject it, right? And you consider that falsifying your null hypothesis. That does not imply that you've proven, or you could even falsify your hypothesis of interest, so your alternative hypothesis. So if you have a hypothesis that this drug does something, you test it by testing that null hypothesis that it doesn't do anything. If you've shown that to be false, you have evidence that it works, but you never actually test your alternative in Nyman Pearson. So it's kind of weird that way. Okay, so that's Nyman Pearson. And you falsify the null, but you don't falsify your actual hypothesis. What if you fail to reject a hypothesis? That means you don't have support for it, but do you falsify it? That is a thing for philosophers of science. Okay, so Bayes, you calculate, all right, here we go. Bayes, we calculate the probability of our hypothesis given our data. So we're actually testing our hypothesis. What would be considered falsifying it? If it has a probability of 0, okay, that actually makes sense. What if you have a probability of 10% that your hypothesis is true? So it's probably not, but it's certainly not certain. So there's an interesting conundrum I see, and I don't see many people talking about it, is that you really don't falsify hypotheses in Bayes as well, except an extreme example, when a hypothesis would have 0 support, okay? But a hypothesis can butt right up against that, say 1%. Does that mean it's falsified? What if it has 50%? It's coin toss. right? So at what point do you consider something falsified, which implies a dichotomous outcome? It's either falsified or not. Are there degrees of falsification? I don't know. All things to think about. So, so it's interesting that, that our big idea of science of being falsifiable isn't actually how we do our science, most of us. Those that collect data that with probabilistic outcomes. Now, if you're a geologist and you have a hypothesis of how evolution works of a timeline, right? You can have a fossil occurring in a certain layer, and that could falsify your hypothesis, but it's not necessarily a probabilistic outcome, okay? So you don't need a whole set of data. If you had a mammal in the Cambrian, it would falsify your timeline that, you know, mammals came about much later. All right, I just find that super interesting that there's a disconnect between what we consider to be science and then how we actually do it every day. All right. All right, let's jump to parameter estimates. So we did this. Make sure I'm covering all our bases. Parameter estimates. So what is a parameter? Okay. A parameter is something we need to estimate from our data. Okay. It's usually associated with a variable, but not always. So I'll give you the outcome we're looking for. Okay. So let's say we want to know the relationship between the amount of a drug and some physiological response. So this would be our physiological response, right? Let's say heart rate. And this would be the amount of caffeine we have. So we observe somebody drinks a cup of coffee with a known amount of caffeine. You measure the heart rate. Another person, more caffeine, less caffeine, heart rate, so on and so forth. So X and Y's, right? Those variables are observed. And from these, what we want to do is build a model, right? Which gives us a slope and an intercept. So we have, and then this is the error, right? Since all of our observations will not fit a perfect line. So we have 1, 2, 3 parameters, okay? And then the question is, well, how do we find this out? Okay, how do we know this? And there might be other times we just want to know what's the average heart rate, right? What is the standard deviation in heart rate, and so on, right? How do we get these numbers? And that's what I mean by parameter estimates. Things we need to estimate, how do we go about estimating them? In some simple cases, like a mean, you can use the arithmetic mean, right? So for example, that's calculated by the sum of y's divided by n. Okay, so we just add up all our observations and divide by the number of observations. Right? It's one way to get the mean. There's only a few parameters you would just plug in and play like this. All right. Other ways to estimate parameters. Okay. Another one, I should say, is least squares. Okay. One of the most frequently calculated number you'll do is a square. And typically a square is some observation minus the mean. Oops. Minus its mean. And then we square it, right? So this is an observation minus the mean of that observation. Let's get to what this means and how we can use it. And actually, a simple case would be the mean, okay? Let's say we have a set of numbers, right? And let's say it's something like heart rate, okay? And we have a set of values, okay? And let's say 70's here, I'll put 60 here, and 80 up here, okay? And these, we'll add one more observation. These are our observations, okay, for different people. And the question is, what is the mean? Well, one way is to add these up, boom, 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 and divide by 5, okay? Another thing we can do is propose a mean, and we'll say 70. And then what you do is, it's 70, or I'm sorry, if we want to calculate it, we would have each observation, right? So let's say this is 79 minus 70, square that, plus this one, which looks like, we'll just say 72, square that, and so on. And you do this for all of it, right? And then you get some number, and that number is the sum of squares, okay? And what you want to do, what the least squares method will do, is it'll find the value of a mean that minimizes the sum of squares, okay? So for these data, let's pick an absurd mean, right? Let's say 90, right? So now you have 79 minus 90 squared plus 72 minus 90 squared, and so on. These numbers are going to be much larger than these numbers. So an average of 90 will not give you the least squares, the least sum of squares, right? That's what that means. The least would be the smallest sum of squares, okay? So that's for the mean. Right? If we want to look at a regression, right? We could have a series of data, right? And then we can, for any intercept, we can have, let's just examine 2 slopes, okay? And the way you calculate least squares here is to take this observation and subtract and square this distance. So we can just look at all these distances, add up those squares, and you get a sum of squares. If this is your proposed slope, then what you have is all these, okay? It's going to be much larger. Nearly every observation is worse off by this line. So this line will not be give you the smallest sum of squares estimate. All right. And the reason why we square, just to review that real quick. Let's go over why we square. Let's go back to our heart rate example. Let's say this is our mean. So you have a large number minus the mean, give you positive, slightly larger positive, right? Now you have, this would be a negative, right? Because now you're subtracting a smaller number from the mean, and you have a negative. And if you were just to sum these without squaring, you come out with something about 0, right? Which makes no sense. So to get around that, you square. So you remove the positive and negatives because you're only interested in the distance between an observation and its mean. All right. Bootstrapping. Bootstrapping means, bootstrapping let me go over what the word means. Imagine you're walking through the woods and you fall into a tiger pit and you are stuck there and you're pretty upset and you wish somebody would come along and pull you out of this. What bootstrapping means is you say, wait a minute, here's what I could do. I can just reach down and pull up my bootstraps and just lift myself out of here. Okay, so which we know isn't possible, but it means to lift yourself out of this. When it comes to data, it means to use your data to test your data. Okay, so let's go back here and we have, let's just say heart rate, and we have a number of observations, right? And I'm going to rescale this, right? 70, somebody's up here, right? So let's say this is 110, right? Everybody was sitting in the office, they took measurements, and for whatever reason, you have this thing up here. Now, if you just took the arithmetic mean, it would be, the mean is pulled up. So it might actually be here. I'm not actually sure, but let's say it's in here, right? But here's the thing, it's weighed by this outlier, okay? So what bootstrapping does is you sample, you have 1, 2, 3, 4, 5, 6 points. A bootstrap, you may say, I'm going to grab 4 points. And here's the thing, with replacement. And you're going to repeat. So in other words, you randomly grab 4 points. So grab this, grab this, grab this, grab this. You take a mean, it's going to be there, right? Then you grab another 4 points. 1, 2, 3, 4. Doesn't have this. That means it's going to go from here to here, right? You keep doing that, and what you'll get is a distribution of means. When you take the mean of that mean, instead of, say, being this mean, it might be here. So it better reflects these data and weighs less the influence of this point. So bootstrapping is really handy when you have data that isn't very consistent, when you have things called outliers. Okay? And we'll try some of these later in lab. All right. So that's bootstrapping. Very, very useful. All right. Maximum likelihood. Okay. I think everybody knows what maximum is. In likelihood, if you remember from Bayes, that is the fit, something that fits. Here would be a parameter that fits the data. So same as in, I think in Bayes I mentioned that it might be the parameter that fits the data as well, but that's what it means here. So maximum likelihood is a method that gives a parameter estimate that is most likely. Okay. And then it's important to know that that likely means fit. And by fit, I don't mean do a lot of push-ups. All right. How do you figure out what parameter has the best fit? Okay. What you do is we need a likelihood function. What does that mean? Well, let's define what likelihood is. So we're going to say the likelihood of some parameter value, like a mean, okay, or a slope, or an intercept, some value, right? The likelihood of that value given y is equal to the multinomial of y I given theta, right? It's, oops, let me fix this here. Probabilities of all yi's given thetas. So this looks like a big pie, right? And what that is, where if you know what sigma is, where it's summing, right? If you had sigma 1 to 3 means add up 1, 2, 3. If you had multinomial, 1, 2, 3 means 1 times 2 times 3. Let's get rid of that because that'll be confusing. So this equals the probability of y1, your first observation, given some parameter, right? So what's the probability of observing, say, 70 heart rate given the average is, say, 72 times, and move it down here, times probability of y2 given theta dot dot dot, and we do that p y n given theta. So for every observation, we figure out the probability of getting that data point, right? So when you do this in practice, your likelihood values, right? Because remember, probabilities can go from 1 to 0. So most of the time they're fractions. So when you multiply a fraction times 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 a fraction, oftentimes you'll get likelihoods that look like this. 0.00000000127, right? Which is pretty crazy, but that's pretty typical, right? You get these absurdly small numbers. All right. So you do this, think about doing these calculations. So you have one theta, and just like least squares, you can propose different thetas and calculate the sums of squares to figure out where it's the smallest. Here you're going to figure out which is the most likely, right? So the sum of the probabilities, right, given a bunch of candidates. Then what you get out is, so let's say this is likelihood, and then you have some values of theta, okay? And let's look at our heart rate. So if you remember, looks something like this, right? I think it was 60 to 80, if I remember correctly. So we can go give some, we'll stay within these bounds. So the probability that the mean is near 60 seems very low, and the probability that the mean is 80 seems very, very low. You think it's most probable that it's here, right? And what you get is something like this, right? So and then what you do is you figure out the tangent line, and that gives you the theta that's most probable. Okay, that's how it's done. So it takes a lot of calculation, because these likelihood functions, you know, in case of 5 points, you would have something like this. You may have likelihood functions that look like this, right? Some weird, takes on a weird shape depending on your data. All right. So as an example in the textbook, what I have is, if you look at the bottom here, you have some data. 0, 0, I think there's another 0 there. Oh no, maybe not. Okay, whatever. There's 3 zeros, 1, 2, 3, 4 ones, 2, 2, 3, 4. When you have counts like this, you can calculate the probability of each one of these observations. So what's the probability? And let's just give an example. Let's say this is the number of deer you see in a field. Okay, so you say, what's the probability of seeing 0 deer, 0 deer, 1 deer, 1 deer, 1 deer, 1 deer? And you want to know what's the maximum likelihood estimate. Well, to figure out the probabilities, here's the formula. The probability of, for example, seeing 0 deer depends on the mean. Okay, so imagine this is very high. The probability of getting 0 is very low. Right? And those probabilities you can calculate for any theta. Okay, so there's how you calculate the probabilities of getting these observations, right? And what I did is let's propose the average is 1, 1.2, or I'm sorry, 1.1, 1.2, 1.3, ... all the way up to 1.6. And what you do is you put a number there for theta, and then you figure out what all these are. So for example, you would have e to the -1, -1, I'm sorry, just 1 to the yi, so yi in this case is 0 over yi. This should be this guy here, and for 0 it's just 0, which equals 1, right? So you calculate this, and then you calculate, that'd be the same thing times this, again times this, and let's just do 2. So you multiply it times the next one, and for 2 it'd be e, and then we're proposing 1 is the mean, so e to negative 1 times 1 raised to the 2 over 2 times 1, right? 4, you put 4 as your y, so here, 4 times 3 times 2 times 1, right? And you do that, and what you get is, let's make some room. So I actually did this by hand, and you get a probability, right? When you multiply out all these probabilities, you multiply them out, and that gives you the probability for 1, and you do it again for 1.1, for 1.2. It is a pain. You get something that kind of looks like this, and I think it was about 1.2. So you have 0 and probably something like 4 over here, and you, oh no, this would, no, not at all. Undo. We did it to 1.6, right? And it ends up that this peaks. So the likelihood, the maximum likelihood is at 1.2. Okay. These can be computer intensive, but most of the time when you run things, it's doing maximum likelihood, and it occurs in a blink of an eye, which is the wonderful thing about computers. All right. That's maximum likelihood. The last thing we'll do is Markov Chain Monte Carlo. A Markov chain is the way you move through sample space. Okay, and so we have these proposed numbers: 1, 1.1, 1.2, 1.3, ... 1.6. So Markov chain means if you have 1.2, right, you can take one step, and then one step. And Monte Carlo means you either go back or forward, okay? And what you're going to do is you're going to do maximum likelihood for a sample of these data, right? So you remember your data is 0, 0, 0, 1, 1, 1, 1, 2, 2, 3, 4. So you pull out a sample, right? And then you calculate the maximum likelihood estimate. Throw those data back. You pull out a sample of data. You pull out a theta. Calculate the probability of that theta given for that sample of data. Throw everything back in. Get your new theta. right? And then get a new sample of data, calculate the maximum likelihood, and so on, and you keep doing that. And what you'll get is what it'll look like in the end. So you'll have theta. What you'll do is you'll sample the sample space for theta, so 1.1, 1.3. And basically what it'll start to do is for any sample, I'll say like getting colder, getting warmer, warm, getting colder, getting warmer, and it'll keep going through. And then what you do is you say, well, what is this average, right? Where you ended up, what is that? And that theta, right? It's like a mean theta. That's what that bar means, is mean theta. And that's your average. What's kind of cool about Markov chain using Monte Carlo is you get a mean, and then you get, so what this looks like if you were to sort of mush this all together, right? Let's erase some of this. Oops. Right. What you get is something like this. And you say, here's my mean theta, but then I also have plus or minus some distribution, right? Some standard deviation. So this is very, very different tactic than these other estimates. So for example, when you do a least squares, okay, you end up with a theta that gives you a least square. And that's what we call a point estimate, right? When you add up the numbers and you divide, right, the arithmetic mean, you get a point estimate, that's your mean. But using Markov chains, you actually get a theta and then a distribution of theta, which is cool. Because the mean is now a variable, okay? And it gives you a good idea of how variable your data is as well. All right, which I think is pretty cool stuff. All right. So 2 very different topics mushed together into one lecture, but there you go. If you have any questions, please let me know by sending me an email or commenting here. All right, take care.